All right, so next up is Sp2 hybridization. So we have three things. So we're going to mix three orbitals. And so we're going to hybridize our 1s electron or orbital and two of our p orbitals. But remember, we have three of them, so there's going to be one left over that's going to be unhybridized. So if we take a look at that kind of energy diagram, we have S, we have P, and we'll go ahead and hybridize them. We're going to form three sp2 orbitals because the number has to stay conserved. And then we're going to have one p orbital left over unhybridized. Let's take a look at the orbitals actually mixing. Right, again, same story as last time, but here we're going to ignore our leftover p orbitals. And so you can see this gives the same trigonal planar arrangement. So that's the same as Vesper. But now what it says is that there's one more p orbital that's unhybridized and sticking out here. And so let's see how that unhybridized p orbital plays a role in bonding and how it controls some of the properties of sp2 hybridized things. So let's take a look at example H2CO. This is formaldehyde. And so if you draw the Lewis structure of this one right here, you see carbon is only attached to three things. So you're predicting an Sp2 hybridization. So let's take a look at what that looks like. So we have this carbon, we have this oxygen, and then carbon's going to have three sp2 hybridized orbitals. So it's going to have a trigonal planar arrangement. So one of them is going to be going like this. One's going to kind of be going out of the board, and then one of them goes back into the board. And each one of these is going to have one electron. And then it has this unhybridized p orbital up here that also has one electron. You're going to have a hydrogen over here. Direct overlap. The hydrogen is going to be overlapping with its 1s orbital. We only hybridize central atoms, not terminal atoms. Another hydrogen there. And then the oxygen is going to bond with this carbon with one of its p orbitals. Again, we only hybridize central atoms. All these other ones are terminals, so we do not hybridize them. So remember, carbon has these 1, 2, 3 sp2 orbitals, and then this one p orbital that's left up like that. And so this so far we have this structure. And so these are what's known as sigma bonds. So it gets the symbol sigma, and in a sigma bond, you have direct overlap of orbitals. But as we can see in this picture, we have a double bond to oxygen. So where's that second bond come from? And basically it comes from another unhybridized orbital of the oxygen and the unhybridized orbital of the carbon. And so they are bonded not because they're directly touching, but because they're kind of like next to each other. And so this is what's known as a pi bond. And it's indirect overlap. And so this stuff's kind of more important for more advanced chemistry that you might get into, and it helps explain why compounds react the way they react and why certain compounds, in order to form bonds, must form them from certain sides and whatnot. But for our purposes, we're just going to say that this explains why sigma bonds are generally more powerful than pi bonds. And that's because there's direct overlap. And so that makes that bond stronger as opposed to weaker. And then the other thing it does, it explains why double and triple bonds can't rotate. So if you're thinking about this bond, I got another picture here for you. So the picture on the left demonstrates the 3 sigma bonds, in which case you see there's direct overlap each time, right? The 3 sigma bonds, all this direct overlap. And then on the right, we see this pi bond, And so if you try to rotate about this double bond, you're going to have to break it, which is shown in this picture right here. So you can see on the left here in this sigma bond, you can rotate while still preserving the overlap of the bonds. And so you can rotate without breaking the bond. Whereas this bond right here, this pi bond, if you tried to rotate it, you'd have to break that indirect overlap and thus break the bond. And so it cannot rotate. So if you tried to rotate, you would break the bond. Which is kind of like a no. So there's Sp2 hybridization. So it helps us explain why pi bonds are weaker than sigma bonds and why pi bonds cannot rotate. And if you get to higher advanced chemistry classes, it'll help explain some reactivities of some compounds. But at that point, you're kind of thinking like organic chemistry.